Good afternoon, everyone. Today, we will be discussing the various reactions of aromatic compounds. However, before we dive into that, it is essential to first understand the criteria that a compound must meet in order to be considered aromatic. Aromatic compounds must satisfy the following conditions. First is its cyclic structure. The molecule must be in the form of a ring. Next is its planar structure, meaning the molecule must be flat or planar. It must also have a fully conjugated system. This requires the molecule to be either sp2 or sp hybridized. A fully conjugated molecule will always be planar. Lastly is the Huckel's rule. This pertains to the number of electrons in the pi system. According to the Huckel's rule, the number of electrons in the pi system must follow the formula 4n plus 2, where n is a positive integer. Please note that n doesn't correspond to any specific number in the molecule itself, so there is no need to look for n within the structure. Only the electrons in the pi orbitals and p orbitals count. So ang electrons nga naa sa sigma bonds kintahay kay dili na siya apil. With these fundamental concepts in mind, we can now proceed to explore the reactions of aromatic compounds. Electrophilic aromatic substitution, or EAS, is an important and unique reaction for aromatic compounds. The following are common types of EAS reactions. We have halogenation, nitration, sulfonation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. All these reactions follow a similar mechanism with only small differences. So, generic mechanism for the EAS, we start by reacting a benzene molecule with an electrophile. The electrophile must be strong because benzene is very stable. To break this stability and disrupt its aromaticity, we need a powerful electrophile to attack the benzene. When the electrophile attacks, a carbocation is formed. This carbocation is stable because it can spread out its charge through resonance. We can show this stability with three different resonance structures. This stable carbocation is called a sigma complex. Let us look at the actual EAS reactions, and we will start with the halogenation reaction. In the general scheme, we can see that we will be needing a halogen. So in this case, we are using a chlorine and aluminum chloride. The aluminum chloride is a catalyst, so motabang na siya sa reaction, pero dili na siya ma-consume during the process. The first step is the formation of the electrophile. While chlorine is electrophilic, it is not strong enough to attack the aromatic ring and break its stability on its own. This is where the aluminum chloride comes in. Aluminum chloride is an excellent Lewis acid, which means it can attract electrons, so it will pull the chlorine towards itself to seal some of its electron density. As a result, a new complex is formed between chlorine and aluminum chloride. The bond between aluminum and chlorine makes the chlorine much more electrophilic. This new complex is now our electrophile, ready to react with the benzene ring. The step 2 is the electrophilic attack. In this step, our newly made electrophile attacks the aromatic ring. So notice that in this attack, ang chlorine nga naa sa tumoy ani nga molecule ang ma-attack. So the attack goes from the aromatic ring on the edge chlorine. That breaks the bond between our chlorines. This attack results in a resonance-stabilized carbocation intermediate, or what we call as the sigma complex. And then finally, we are going to restore the aromaticity by removing the proton from our carbocation intermediate. The leftover catalyst, aluminum chloride, that now holds an extra chlorine atom helps with this step. The proton is removed and we end up with the final product, chlorobenzene, along with the regenerated catalyst, which is the aluminum chloride, and hydrogen chloride as the byproduct. The next reaction we are going to tackle is the nitration of aromatic compounds. In this reaction, the main reagent is nitric acid, and sulfuric acid acts as the catalyst. Just like in the halogenation reaction, nitric acid on its own isn't electrophilic enough to attack the aromatic ring. It needs a little help to make it strong enough to react. As with the previous reaction, the first step in nitration is the formation of the electrophile. Since stronger acid ang sulfuric kaysa sa nitric acid, magsugod ang reaction by proton transfer from sulfuric acid to the oxygen of the nitric acid. This creates a protonated nitric acid, which is unstable. The protonated nitric acid undergoes the leaving group dissociation, and in this case, it quickly loses water, forming the nitronium ion. This nitronium ion is now our electrophile, ready to attack the aromatic ring. The nitronium ion is a strong electrophile, so it easily attacks the aromatic ring. This leads to the formation of the resonance-stabilized carbocation intermediate, just like we saw in the halogenation reaction. The final step is to restore the aromaticity of the ring by transferring a proton from the carbocation intermediate. The leftover conjugate base from sulfuric acid helps with this step, and in doing so, it regenerates the sulfuric acid catalyst. This leaves us with a final product, nitrobenzene, along with the regenerated catalyst.
Good day everyone. Today I will be presenting a report on nucleophilic aromatic substitution or NAS. So what is NAS? Nucleophilic aromatic substitution or NAS is a reaction where a nucleophile replaces a leaving group in an aromatic ring. Unlike electrophilic aromatic substitution, which involves an electrophile attacking an electron-rich system. NAS occurs when the ring is electron deficient, making it more susceptible to nucleophilic attack. There are two mechanisms of NAS: the addition-elimination mechanism and the elimination-addition mechanism. The addition-elimination mechanism starts with a nucleophilic attack on the electron-deficient ring, leading to the formation of a Weissenberg complex. This negatively charged intermediate stabilizes before the leaving group is eliminated. In the benzene mechanism, a strong base removes a proton adjacent to a leaving group, forming a highly reactive benzene intermediate. A nucleophile then attacks the benzene, leading to substitution. This pathway is less common but occurs under harsh conditions. So when it comes to the electrophilic aromatic substitution, we are going to take the hydrogen from our molecule and we are going to replace it with some sort of electrophile. Now, on contrary, when it comes to the nucleophilic aromatic substitution, we gotta have an aromatic molecule with some sort of leaving group. And typically, that leaving group is going to be some sort of halide like fluorine, chlorine, bromine, and iodine. Now, we are going to take this molecule and we're going to treat it with some sort of nucleophile. And as a result, we're going to replace that leaving group with whatever nucleophile we're dealing with. So, let's talk about the mechanism of the nucleophilic substitution. I'm going to take this aromatic compound that I have over here with the nitro group and chlorine, and I'm going to treat this molecule with potassium methoxide. Doing the preliminary analysis of molecule, I can see that the chlorine in this case is going to be our typical leaving group. So probably I'm going to replacing this chlorine over here, and of course the methoxide here is going to be my nucleophile. So at the very beginning, the reaction starts by taking our nucleophile and doing the nucleophilic attack, like giving me the following negatively charged intermediate. Just like what we saw in the electrophilic aromatic substitution, here resonance is going to play a huge role. So I can draw multiple resonance structures here, starting by taking my electron and moving them around the ring like this, giving me the following structure. Then, from this point, I can take them and move them one more time, giving me the following intermediate. And then, finally, from this point, I will also remember that the nitro group is not just a bunch of random atoms, but it does have a structure which is very relevant for the resonance. So I can draw another resonance structure involving my nitro group, which is going to look like this. And in this case, I want to point out something very important because my negative charges are on the oxygen in the last structure. And it is going to be a major resonance contributor, and it is going to be fairly important for our mechanism overall. Now, we are going to move on the elimination part in which we are going to be losing our leaving group. We can show the loss of the leaving group by showing how these electrons going to kick back and displace this chlorine essentially out of our molecule, giving us the final product looking like this, and a Cl- just floating around minding its own business. There are a couple of extremely important points here that we need to talk about. First of all, the electron withdrawing group. Let me redraw the first part of mechanism here where I have all those negatively charged resonance structure moving around. The nitro group here is serving a crucial and probably the most important role. It is there to stabilize the negatively charged. Now, let's imagine a situation where my nitro group is incapable of stabilizing the negative charge. So let's compare the reaction that I have on the top of the screen with the following reaction here. My methoxide can still potentially attack the position where my leaving group is. So this attack here, the electrons go down like that. And as a result of this nucleophilic attack, I'm going to get the following intermediate. Now, of course, this intermediate can show me a few resonance structures. I can take this electron and move them around like giving me the following intermediate. And from this point, I can move them around one more like this, giving me another resonance contributor. Now, the problem here is that I have exhausted all of my resonance contributors, any reasonable resonance contributors, and the issue is that it is not enough to effectively stabilize our negative charge. The nitro group was absolutely crucial for that, and now we don't have the nitro group stabilization. So if we think about this reaction from the purely kinetic perspective, I can draw a reaction diagram, which is going to look like this. Now, I have the activation energy for this reaction for meta position, and I have the activation energy for the order para position. Of course, the activation energies for the auto para are not going to be exactly the same. I'm just combining ortho and para together for the simplicity's sake. So in this case, since the activation energy for the meta position is so much higher due to the fact that our intermediate is not well resonant stabilized, that means that the reaction is going to be significantly slower. Not impossible, but too slow for practical applications. So remember, when it comes to the placement of your leaving group and your electron withdrawing group, those guys must be your autopara to each other. And I will remind you here real quick that the typical electron withdrawing groups are your meta directors that you know and love from the electrophilic aromatic substitutions. Things like NO2, nitriles, carbonyls, etc. Anything that pulls the electron density towards itself. Now, in addition to the electron withdrawing group and the proper placement of the electron withdrawing group in the molecule, the nature of our leaving group matters as well. So normally, when we are talking about the leaving groups and we are ranking our leaving groups, usually we think that iodine is the best leaving group. Then we have bromine, chlorine, and fluorine is such a horrible leaving group that generally speaking, we say that fluorine is not even a viable leaving group to begin with. However, when it comes to the nucleophilic aromatic substitution, the trick here is to keep in mind is that the rate determining step or the rate limiting step, if you like, in the nucleophilic substitution is the nucleophilic attack itself. So if I look at my molecule where X is my leaving group, the nucleophile is going to be the attacking at this position where we are developing a partial positive charge due to the polarization, due to this X that is sitting here. And here's the thing, the higher the delta plus, the better and the easier the attack is going to be. And of course, the polarization that delta plus is going to scale with the electronegativity. So let's pull up our periodic table and check out our electronegativity. For the iodine, the electronegativity is about 2.66. For bromine, it's already bigger, it's 2.96. For chlorine, it's even bigger, it's 3.16. And finally, for fluorine, it's almost 4 out of 4. So when it comes to our leaving groups, the fluoride or fluorine here, however you want to think about that, going to create the highest delta plus on the carbon, which means for the purposes of the nucleophilic aromatic substitution, the fluorine is the best leaving group. And in this case, instead of thinking about our leaving groups from the perspective of the leaving group ability, we should be thinking about those from the perspective of the reactivity towards the nucleophile. A strongly electron withdrawing fluorine is going to make the carbon to which is attached very electrophilic, making reaction with nucleophile very favorable. So this way, whenever you are thinking about radioselectivity of nucleophilic aromatic substitution in general, the very first thing we are going to check is going to be the position of our leaving group and our electron withdrawing group. The electron withdrawing group and the leaving group, those guys must be orthopaired to each other. Then, if we're still in doubt which leaving group to choose, we're going to go with the fluorine, then chlorine, then bromine, and finally, if we have no other choices, that's going to be iodine. Comparison between NAS and EAS. NAS and EAS are two different substitution reactions in aromatic chemistry. NAS occurs in electron-deficient systems with nucleophiles, while EAS occurs in electron-rich systems with electrophiles. The intermediates and conditions also differ.
The amino group aniline reacts with bromine water without catalyst to yield the tribromonoaniline. Sodium bicarbonate is added to neutralize the hydrobromic acid that is also formed. The summary activators. Here are the groups and here are the compounds: phenooxide, anilines, phenol, phenyl ester, analytes, and lastly, the alkylbenzene. The alkylbenzene groups have no lone pairs. Next is activators and deactivators. This is the ortho and para strongly affected. If the substituent on the ring is electron donating, the ortho and para position will be activated. This one, electron donating, activated. If the group is electron withdrawing, the ortho and para position will be deactivated. This one, electron withdrawing, deactivated. Next is nitration and nitrobenzene. Electrophilic substitution reaction for nitrobenzene are 100,000 times lower than for benzene. The product mix contains mostly the meta isomers, only small amounts of the ortho and para isomers. This is nitrobenzene, nitric acid, and 100 Celsius on sulfuric acid to dinitrobenzene. The dinitrobenzene composed of ortho 6%, meta 93%, para 0.7%, total of 99.7%. Next is ortho and substitution on nitrobenzene. The group is a strongly deactivating group when considering its resonant form. The nitrogen has always a formal positive charge. Ortho or para addition will create an especially unsustainable intermediate. Next is meta substitution on nitrobenzene. Meta substitution will not put the positive charge on the same carbon that bears to nitro group. Next is energy diagram. Nitrobenzene to benzene, nitrobenzene to meta, nitrobenzene to ortho or para. And next is the activators and meta directors. Most electron withdrawing groups are the activators and meta directors. The atom attached to the aromatic ring has a positive or partial positive charge. Electron density is withdrawn inductively along the sigma band. so the ring has less electron density than benzene, and thus it will be slower to react. Next is ortho attack of acetopenone. In ortho and para substitution of acetopenone, one of the carbon atoms bearing the positive charge is the carbon attached to the partial positive carbon, nil carbon. Since, like charges repel, this closely proximity of two positive charges is especially unstable. These are positive charges adjacent and favorable, and these are positive charges here in other resonance. Next is other deactivators. Group is nitro, the resonance forms, and the example is nitrobenzene. Then next is sulfonic acid, the resonance forms, and example is benzene, sulfonic acid. The next is cyano. This is the resonant form, and the example is benzonitrile. Next is ketone or aldehyde, and this is the resonant form, and the example is acetopenone. Next is ester, then resonant form, and the example is methyl benzonate. Then lastly is the quaternary ammonium. This is the resonant form, and the example is trimethylaniline iodide. Next is nitration of chlorobenzene. When chlorobenzene is nitrated, the main substitution products are ortho and para. The meta substitution product is only obtained in 1% yield. The chlorobenzene to nitric acid and sulfuric acid to ortho with 35% plus meta 1% plus para 64%, total of 100%.
Inductive effect. Halogens like chlorine, bromine, iodine are electronegative atoms. They pull electrons, so they are electron withdrawing groups by inductive effect. So they pull electron. When attached to a benzene ring, they pull electron density away from the ring through the sigma bond, the single bond connecting the halogen to the ring. This electron withdrawal deactivates the ring towards further electrophilic aromatic substitution reactions. Reaction where an electron-rich group replaces a hydrogen on the ring.
Halogens are ortho-para directors. Resonance effect. The lone pairs on the halogen can be used to stabilize the sigma complex by resonance. So, this is the ortho-meta-para positions in a benzene ring. So, this is an example of orthoresonance. So, here's the trick, guys. If an electrophile is located at the ortho position, there will be carbocation in the left and right side alternately. So, carbocation skip, carbocation skip. So, this will be applied to ortho, meta, and para position. So, here's the summary.
This diagram illustrates the relative energy changes during the electrophilic aromatic substitution reaction on a benzene ring with a chlorine substituent. Summary of directing effects. The table categorizes substituents based on their directing effects in electrophilic aromatic substitution. This image discusses the effect of multiple substituents on electrophilic aromatic substitution reactions. It builds upon the previous concepts of directing effects, ortho or para versus meta. These present an example reaction where p-nitrotoluene undergoes nitration. The key point is that the methyl group is ortho or para directing while the nitro group is meta directing. In this specific case, the ortho directing effect of the methyl group is stronger, resulting in the major product being the one with the second nitro group in the ortho position relative to the methyl group. This emphasizes that the directing effects of multiple substituents can reinforce each other. In this slide, it shows the nitration of silane. So here, both metal groups are ortho or para-directing. However, the position between the two metal groups is sterically hindered, making substitution at that position less favorable. The major product is the one where the new nitro group is ortho to the one metal group and para to the other. The steric hindrance between the two metal groups is highlighted as a factor affecting the reaction outcome. This section addresses situations where the directing effects of multiple substituents oppose each other. The example shows a molecule with a nitro group, meta-directing and deactivating, and a methoxy group, ortho or para-directing and activating. Competing effects. The nitro group wants to direct the incoming bromine to the meta position, while the methoxy group wants to direct it to the ortho or para positions. Dominant influence. The nitro group is deactivating and meta-directing, while the methoxy group is activating and ortho or para-directing. Because the methoxy group is significantly stronger activator than the nitro group is a deactivator. The bromine atom is directed to the ortho and para positions relative to the methoxy group. The slide highlights that when directing effects oppose each other, the most powerful activating group dominates. Friedel-Crafts alkylation involves the addition of an alkyl group, the R, to a benzene ring. This reaction requires an alkyl halide, R to X, where X is halogen like chlorine, bromine, or iodine, and a Lewis acid catalyst like silver chloride or ferric bromide. The Lewis acid reacts with the alkyl halide to form a carbocation, R+, which is a strong electrophile. This carbocation then attacks the benzene ring, leading to the alkylated product. The Lewis acid is crucial because it helps generate the electrophilic carbocation. This reaction is important because it allows for the building of more complex molecules from simpler ones. This image details the mechanism of Friedel-Crafts alkylation reaction, a three-step process. Protonation of alkenes. This section describes how an alkene can be protonated, adding a proton, using hydrogen fluoride as an acid. So, what is the reaction? The alkene's double bond acts as a nucleophile, attacking the proton of HF. This forms a carbocation intermediate. So, why HF? It emphasizes using HF because the fluoride ion is a weak nucleophile. This is important because a strong nucleophile would react with a carbocation, preventing the desired reaction from proceeding. With HF, the carbocation is more likely to react with another molecule like a benzene ring in a Friedel-Crafts reaction before being attacked by the fluoride ion. Alcohols and Lewis acids. This section shows how alcohols react with Lewis acids, specifically boron trifluoride. So the reaction here, boron trifluoride, a Lewis acid or electron acceptor, coordinates with the oxygen atom of the alcohol. This coordination forms a complex where the oxygen becomes positively charged. Carbocation formation. The subsequent loss of proton from the alcohol generates a carbocation. This carbocation can then participate in other reactions. So there are three key limitations of Friedel-Crafts alkylation.
So first, reaction fails if benzene has a substituent that is more deactivating than halogens. Rearrangements are also possible. And lastly, the alkyl benzene product is more reactive than benzene, so polyalkylation occurs.
Good afternoon, ma'am and classmates. Today I will be discussing about rearrangement to nucleophilic reactions. So, rearrangement of nucleophilic reactions. Rearrangement to nucleophilic reactions, often involving SN1 mechanisms, occur when a nucleophile induces the migration of an atom or group within a molecule, leading to a more stable carbocation intermediate before substitution. So, ang rearrangement to nucleophilic reactions Often ni siya nag-involve as SN1 mechanism. Mo-occur ni siya when mo-migrate ang atom or kanang group within a molecule, dayon mo-migrate ang atom para mo-form og more stable na carbocation para maka-form og product or compound. So, when we say carbocation, it is an ion with a positively charged carbon atom. Nag-act ni siya as a highly reactive electrophile. Kabalo naman taon sa electrophile. And ang nucleophile kay naano sa word itself, nucleus-loving nucleophile. Means na attracted siya sa positively charged or electron deficient na mga sites. So, diba, sa previous slide, nag-talk ta about rearrangement sa nucleophilic reaction. Ang rearrangement sa nucleophilic reactions ga-involve og SN1 mechanism. Ang SN1 mechanism is substitution nucleophilic unimolecular. It describes a two-step nucleophilic substitution reaction where the rate-determining step involves the unimolecular dissociation of a living group, forming a carbocation intermediate followed by the nucleophile attacking the carbocation. Karon, mag-talk ta about sa mechanism sa rearrangement of nucleophilic reactions. Una na kaning unang step na mahitabo is ang leaving group departure. The reaction begins with the departure of a leaving group, example a halide, or mag-give kog other example bromine. I will give an example later and we'll discuss it. For now, mag-discuss ako about sa mechanism. So, moto, leaving group departure. Example, ang halide, mo depart siya para forming a carbocation intermediate. Then next, mahitabo na ang rearrangement. If the carbocation is unstable, example primary, a rearrangement can occur to form a more stable carbocation secondary or tertiary. So, ang carbocations, naa siya murag kuan sa stability. Ang primary, secondary, ang tertiary. Ang tertiary mo ang pinaka-stable while ang primary mo ay pinaka-less na stable na carbocation. And then last sa rearrangement sa nucleophilic reaction kay ang nucleophile kay mo-attack. Once a stable carbocation is formed, the nucleophile can attack leading to the substitution product. So, if mo-attack na ang nucleophile sa carbocation na stable, mo-form na ang substitution na product. Now, let's move on to the rearrangement types. So, ang rearrangement types kay sa nucleophilic reactions kay naay two types. Muni ang hydride shift ug ang alkyl shift. Rearrangement involves the migration of a hydrogen atom na ang hydride shift, gitawag og hydride shift, or an alkyl group or alkyl shift from an adjacent carbon to the positively charged carbon. Why rearrangement occurs? Rearrangements allow the formation of more stable carbocations which are more reactive and lead to the formation of a different product than what would be expected from the initial carbocation. So, mahitabo ang rearrangement para mo form og more stable na carbocations. So now, mag-show ko sa inyo og common pattern sa rearrangement to nucleophilic reactions. So, mo ni siya, isa, na ako'y 3 na ihatag. And dali ra siya masabtan guys, I assure you. So muna siya. Oopsie. Ang tawag ani na this structure kani atong primary na carbocation kani siya guys. Kana siya primary carbocation. Kana siya is 2-methyl-butyl carbocation. Ang mga primary carbocations kay unstable tungod kay they lack electron donating support from surrounding carbo atoms, I mean. So, kanina rearrangement kani sa primary kay ang mahitabo ani na step is ang hydride shift. 'Di ba nagkuan ko before na ang hydride shift kay muni ang movement sa hydrogen within sa anina arrangement. So, 'di ba? As you can see, nakaning arrow na green na ang hydrogen kay nasa kuan primary which is ang kanang 1. And then ma-shift na siya, mo transfer na siya kung asa ni kani siya guys, kaning plus, kanang plus mo na siya ang carbocation. Manay kuan sa carbocation, basa na siya. Carbocation na siya ng plus kini. Yeah. And then na-I shift na mahitabo para ma-stabilize ang charge. So, manani ang product na to, manani. So, 'di ba, kailangan man mo na-I rearrangement para mo more stabilize ang carbocation. So, from primary to secondary. As you can see, dali raman siya masabtan. Ang H here before ni transfer siya diri sa primary ay sa secondary here kani mao ni ang sunod na pattern guys. Ang primary kay mo shift sa tertiary na carbocation. So, diba, makita na to diri ang hydrogen na sa first na carbon. Dayon, sa atong product, diri kani siya, kanina carbocation, kani siya, carbocation, muna siya ang tertiary, diba? So, ni-move siya sa ikatulo. 1, 2, 3, na siya diri. Ang tertiary na carbocations kay very stable because the surrounding carbon atoms kay mo help distribute sa charge. And here guys, ang last na common na pattern is secondary to tertiary na punta. Kung asa ang secondary na kung asa nakalukit ang kaduha na carbon, ni-move siya sa ikatulo ng carbocation. So, manani ang product. Kani tanan na patterns na kung gipakita ninyo guys, kaning primary to secondary, primary to tertiary, and secondary to tertiary, kay puro ni sila SN1, diba? SN1 kay kanang mga ang reaction na two-step ra siya. See, makita nato diri. Hard siya ka step. First step, then mani ang second step. So, karon guys, magpakita na ko ang example sa rearrangement of nucleophilic reaction. Ang example na to kay 2-pentanol. So, here sa una na compound, ang tawag ani niya na compound is 3-bromo-2-methylpentane. And ang atong final product is 2-methyl-2-pentanol. Ang kaning H2O mo act as a nucleophile. Muna siya ang nucleophile sa ato ang kanina rearrangement na reaction. Kanina rearrangement kay nagpakita og carbo-cation rearrangement. Kung asa ang bromine kay initially siya na-attach diba diri na compound kani si bromine kay na-attach siya na compound og ma-replace siya og hydroxyl OH gikan sa water. Tapos ma-form ani na compound kani si methyl 2-pentanol 2-methyl-2-pentanol rather. Kuan ako guys para maka-drawing ko usab. So ang una na mahitabo kay ang bromine kani siya ang bromine kay living group na siya, diba? Ako nang gi-discuss ko ganiha living group. Ang mga living group kay dali ra na mo detach. So si bromine dali ra siya mo detach which is naka-attach siya sa carbon number 3 kani. When bromine leaves, it creates a carbocation at carbon number 3. Unstable man si carbon 3 so need og rearrangement para mas stable. So ang step sa rearrangement kay hydride shift ni siya kanina diri na rearrangement. Ang shift kay hydride shift. Ang atong water which is ang nucleophile kay mo attack siya sa positively charged na carbon mo attack sa positively charged na carbon. Since sa water, ang oxygen kay na may lone pair electrons, mo stabilize ang charge by forming a bond ni carbon. And then, here sa atong final product which is ang 2-methyl-2-pentanol na compound, kay na siya hydroxyl kaning OH attach sa carbon number 2 instead sa bromine. Kay sa carbon number 3 guys, kani sa carbon number 3, secondary manggod di ang carbocation. So, di ba, ang tertiary na carbocation kay mas stable man kaysa sa secondary. So, mao to, na siya here. Kanina substitution is nucleophilic, where ang bromine kanitong bromine kay na-replace og hydroxyl. And that would be all sa ako ang part. Thank you for listening. And unta ka sa mo.
Chlorinization of benzene. Addition to the benzene ring may occur with excess of chlorine under heat and pressure. The first chlorine added is difficult, but the next 2 moles added rapidly. Normally, benzene is resistant to addition reaction due to its stable aromatic structure. However, under excess chlorine heat and pressure, chlorine can add to the benzene ring rather than substitute hydrogen atoms. The first chlorine addition is difficult because it disrupts benzene's stable aromaticity, but once that happens, the next 2 molecules of chlorine add more easily. This leads to the formation of lindane or the hexachlorocyclohexane, which is an insecticide. Next is the catalytic hydrogenization of benzene or the reduction reaction. Hydrogenization means adding hydrogen to benzene to break its double bonds and convert it into cyclohexane or a substituted cyclohexane. This reaction requires high temperature, which is 100 degrees Celsius, high pressure, which is 1000 pounds per square inch, and a metal catalyst like platinum, palladium, nickel, ruthenium, or rhodium. Once hydrogenization starts, it cannot be stopped at an intermediate stage. The benzene ring will be fully reduced to a saturated ring or cyclohexane. The example in the slide shows 1,2,3 trimethylbenzene being converted into its fully hydrogenated form. Step 3. Protonation, addition of proton from alcohol. A proton from alcohol attaches to the ring, partially breaking aromaticity and stabilizing the radical. Step 4. Second electron addition. Another electron is added, further reducing the system and forming a carbon ion or a negatively charged carbon structure. The last step is the step 5, which is the second prot- for the last step is the step 5, which is the second protonation or addition of proton from alcohol. Birch reduction. Birch reduction is a reaction that partially reduces benzene or other aromatic rings into a non-aromatic compound called 1,4-cyclohexadiene instead of completely hydrogenating benzene, as in catalytic hydrogenization. It only breaks two of the three double bonds, leaving a partially reduced product. Here are the step-by-step mechanism of Birch reduction. Step 1. Formation of solvated electrons. When sodium or lithium dissolves in liquid ammonia, it releases electrons, creating a deep blue solution. These free electrons act as reducing agents. Step 2. First electron addition. One electron is added to the benzene ring, creating a radical anion, a structure with an extra electron, making it negatively charged. Step 3. Protonation, addition of proton from alcohol. A proton from alcohol attaches to the ring, partially breaking aromaticity and stabilizing the radical. Step 4. Second electron addition. Another electron is added, further reducing the system and forming a carbon ion or a negatively charged carbon structure. The last step is the step 5, which is the second protonation or addition of proton from alcohol. Another proton from alcohol attaches, resulting in the final product, which is the 1,4-cyclohexadiene or a ring with two double bonds. Limits of Birch reduction. Birch reduction works well with simple benzene rings, but certain substituents affects the reaction in different ways. First, electron withdrawing groups. Example is the COOH. If a carbon group is attached to the benzene ring, Birch reduction occurs efficiently. The electron withdrawing effect of the carbonyl group stabilizes the intermediate anion, making reduction easier. For example, benzenoic acid reduced to 1,4-cyclohexadiene with carbonyl group attached. Second is the electron donating groups. If a methoxy group or another electron releasing group is attached, the reaction is less efficient. This group destabilizes the intermediate anion, making reduction harder. For example, anisole undergoes Birch reduction but with lower yield, negative 85%. Next is the side chain oxidation. Side chain oxidation is a chemical reaction in which an alkyl group attached to a benzene ring is completely oxidized to a carboxyl group using strong oxidizing agents. What happens in the reaction? If you have a benzene ring with a side chain like ethylbenzene or propylbenzene, the entire side chain gets converted into a carboxyl group, no matter its length. This occurs only if there is at least one hydrogen atoms on the benzylic carbon, the carbon directly attached to the benzene. Next is the side chain halogenation. Is a chemical reaction where a halogen atom like bromine or chlorine is added to a carbon atoms in the alkyl side chain of an aromatic compound like toluene. The reaction requires light to initiate it. Benzylic position, the carbon atom directly attached to the benzene ring is called the benzylic position. This position is the most reactive in the side chain halogenation. Next is bromination. Bromine is highly selective. It primarily reacts with the benzylic position, leading to a single major product. Next is chlorination. Chlorine is less selective than bromine. It can react at multiple positions on the side chain, resulting in a mixture of products. Here is the mechanism of side chain. Next is the SN1 reaction, or the unimolecular nucleophilic substitution. It is a two-step mechanism where a living group like bromine or chlorine first departs, forming a carbocation which then reacts with a nucleophile. Why benzene halides undergo SN1 easily? The benzene carbocation is highly stabilized by resonance, making it very easy to form. This increased the likelihood of an SN1 or the unimolecular nucleophilic substitution mechanism even in protic solvents like water or alcohol. Next is the SN2 reaction or the bimolecular nucleophilic substitution. The SN2 reaction is a one-step mechanism where the nucleophile affects the substrates and displaces the living group at the same time. Why benzyl halides are highly reactive in SN2. The transition state is stabilized by the benzene ring due to overlap with pi electrons. This makes benzyl halides almost 100 times more reactive than primary halides. Unlike SN1, SN2 reaction requires a strong nucleophile and a polar aprotic solvent. The last is the oxidation of phenols. Phenols can be oxidized to quinones, which are conjugated 1,4-diketones. Common oxidizing agents: sodium dichromate in sulfuric acid. Oxygen from air can also slowly oxidize phenols. For example, oxidation of 2-chlorophenol to 2-chloro-1,4-benoquinone. Quinones are biologically significant molecules found in vitamins, coenzymes, and dyes. They act as electron carriers in biological systems.